Okay, so continuing here with atomic structure and chemical bonding. Now, we are now going to look at isotopes. Now, what are isotopes? What's a definition, or what can we say isotopes are? So, when you're talking about isotopes, you have got atoms of the same element. Atoms of the same element. So, I'm going to see this element. Let's say this element is X. And you have got another one. This same element is X. Okay. Now, these two are atoms. Now, when you're talking about atoms, atoms are simply the smallest indivisible particle of an element. Smallest indivisible particle of an element. And then an element is a pure substance that cannot be split into two or more chemical substances by any chemical mean. So, what we are saying is when you've got this, you can see both of them are X's, meaning they are all atoms. Okay, it's the same element because you can see they have got the same symbol. But remember, we said for an atom, we have got a mass number and the proton number. I'm going to put the proton number on down. Z is the proton number; it represents the number of protons, and then A is the number of neutrons plus protons. So we are saying A, that is the mass number, is given by Z, which is the proton number, plus neutron number. So in this case, when you see an atom like this, you've got X. Let me just use a common carbon. You have got carbon. Carbon has got 6 protons, but you are going to have carbon 12, carbon 13, and also carbon 14. So you can see that the mass numbers are different, but you have got the same atomic or proton numbers. So isotopes are atoms of the same element with the same proton or atomic numbers but different mass numbers. Now, why is it that they are different mass numbers? You can see that for us to get the mass number, we need to add the atomic number with the neutron number. So since the atomic numbers are all the same, you can see they are all sixes in everything. That means the number of neutrons are going to be different. So you can also say an isotope isotopes are atoms of the same element with the same atomic number but different neutron numbers. If you don't want to say different neutron numbers, you can say different mass numbers. It's all the same thing, because if this is different, then that means this is going to be different. So these are isotopes. So we have got different isotopes. We've got isotopes of carbon, we've got isotopes just like you've seen here, we've got isotopes of hydrogen just like that. Okay. So in a case of hydrogen, let me just give an example of that one. So we have got hydrogen 1, hydrogen 2, and hydrogen 3. So these are all different forms of hydrogen or different atoms of the element hydrogen. Hydrogen 1, hydrogen 2, and hydrogen 3. Of course, all of these, the proton number is the same. They have got the same number of protons in all of these. Now, meaning that firstly here we've got one proton. Even here we still have one proton. Even here we still have one proton. But what is only differing is what? The mass number. Meaning that you know that for us to get a proton number, it is given by, the mass number is given by proton number plus neutron number. So if we have already a proton number of 1 here, and this is also giving us a 1, meaning that the number of neutrons are what? 0. So in hydrogen 1 we don't have any neutron. In hydrogen 2 we have got 1 neutron. In hydrogen 3 you have got 1 neutron. How do you find the number of neutrons? You are just going to use the same formula. So where there is A, that is the mass number, we are going to put a 3. And this is going to be where there is Z, that's a proton number, we're going to put a 1, and then plus N, we want to find N, so we're going to take 1 the other side. So that is going to be 3 minus 1, and that is going to be N, meaning that N is equal to 2. So that is how we get that. Okay, so the 3 isotopes of hydrogen you've seen here are also called ordinary hydrogen. So the first one, which we call the ordinary hydrogen, has got only one proton and also no neutron. This is called ordinary hydrogen with a mass number of 1. The second hydrogen, the one with a mass number of 2, is called deuterium. The hydrogen with a mass number of 3, this is called tritanium or tritium, however you can pronounce it. So these are the three types of isotopes of hydrogen. So in the nucleus, everything is the same. Now just outside, that is, just adding the protons and the electrons, the protons and the neutrons. I said in the nucleus everything is the same, not really in the nucleus, but protons are the same, because in the nucleus this is where we find also protons, meaning that if we want to look at in the nucleus of this one here, what you are going to see is we only have a proton in the nucleus. But when it comes to this one, you have got a proton, you also have a neutron. When it comes to this one, you have got a proton, but you have got two neutrons. So you can see that in the nucleus, what is only the same is what? The protons. Okay. So let's say they've given us a substance. They have said this substance is X3 minus, and then they've told us it has got, let's say, 7 protons. Let me say 7 electrons. The question is, how many protons does it have? So look at it. It is X3 minus, but it has got 7 electrons. How many protons is it going to have? Well, the question is, how do we find the number of protons? Now, you just look at the formula itself. This is X3 minus. It has got 7 electrons. So if X3 minus has got 7 electrons, how about X itself without a 3 minus? Now what does the 3 minus mean? 3 minus means something has what? Gained. Remember, when something is negatively charged, it means it has gained electrons. So before it gaining 3 electrons, how many electrons did it have? Before it gaining those 3, how many did it have? So what you are going to do is just say 7 minus 3, meaning that it had 5 before gaining. Okay, 5 electrons. So if something has got 5 electrons and then it gains 3 electrons, it's going to become 3 minus. Whenever something gains, it becomes 3 minus. So you look at the one that is not charged. You are going to look at this one. The number of electrons in the non-charged particle is equal to the number of protons, meaning that this compound has got 5 protons. So you look at the one which is not charged. Okay. The number of protons and the number of electrons in a neutral atom, they are equal. So if they've given something that is charged, just make sure that you do this. Okay, let's say we've been given this one. We've been given Y, let's say 2 plus, and then this one has got 6 protons. Now the question is, how many electrons does this one have if it has got 6 protons? Well, the first thing is, let's find out how many protons are going to be in Y without a charge. Now the number of protons are always the same, whether something is charged or it is not charged. They are always what? The same. So if this one has got 6 protons, meaning that even this one down is going to have what? 6 protons. So in the neutral one, we can see here the number of protons are equal to the number of electrons. So I've got 6 electrons, which is equal to 6 protons in the neutral one. Now if you look at this one, it has got a charge of positive 2, meaning that we have lost 2. Whenever you see a charge of positive, meaning we have lost 2. So because we have lost 2 electrons, from these 6 we are going to remain with how many? 4. So meaning that you only have 4 electrons in this one. So this is how you get to look at isotopes. Okay. Now how do we get to find okay, what are the uses of isotopes? How do you use isotopes? We've seen that isotopes are atoms of the same element with the same proton number but different mass numbers. How do we get to use isotopes? So the first use of isotopes is that, for example, hydrogen isotopes are important in the study of nuclear energy. We have got what is called nuclear fission and nuclear fusion. So when the nucleus of hydrogen splits or when it joins, so to fuse is to join and then fission is to split. When it splits or merges, these are going to release a lot of energy, and this is why you have got those bombs we see. So that is the importance of what isotopes or the application of isotopes. Okay. Apart from that, in the study of energy, some isotopes are artificially made by firing neutrons or protons at elements. So these usually emit radioactive rays which are called radioisotopes. Now, when I'm talking about these radioisotopes, they are used as tracers. Okay, radioisotopes are used as tracers to investigate such things as the flow of liquid in chemical plants and for the study of wear in machines. So in tracers, for example, if there is a destruction in a certain machine, you are going to use isotopes to be able to see that. Isotopes are also used because they also get to kill cancer. They also kill cancer. So that is one also importance of isotopes. So these are some things that we need to know on the application of isotopes. And also for carbon dating, for example, the carbon 14 isotope, it is used to see how old something has lived. For example, you get bones of some things which lived some years ago, so you can use an isotope. Okay, so here also we need to understand what is called relative atomic mass. Now, when we are talking about relative atomic mass, the symbol is A with a small r. Relative atomic mass is simply the number of times that the mass of one atom of the element is greater than 1 over 2 of the mass of an atom of carbon 12. So when you're just talking about relative atomic mass, is the mass of an atom compared to 1 over 2 of the mass of carbon. So this is relative atomic mass, mass of an atom compared to 1 over 2 of the mass of carbon. Okay, so this is relative atomic mass. For example, the relative atomic mass of oxygen is 16. So you are going to see the relative atomic mass of oxygen is 16. Let me put it here. So what does this mean if we say that the relative atomic mass of oxygen is 16? Meaning that oxygen has a mass 16 times heavier than 1 over 2 of the mass of carbon. It has got a mass of 16 times heavier than 1 over 2 of the mass of carbon. So that's the meaning. So if you get carbon, its mass, let's say the mass of carbon is 24 grams. Okay, the mass of carbon is 24 grams. So we're going to say 1 over 12 of 24. This is going to give us what? This is going to give us 2. So meaning that oxygen is 16 times heavier than these 2 you are seeing here. That's the meaning. So that's relative atomic mass. Now, because we have got isotopes, because of the isotopes which we have, there is a formula that we use when you want to calculate the relative atomic mass of an isotope or of an element. For example, when you get hydrogen itself, you have got hydrogen 1, you have got hydrogen 2, you have got hydrogen 3. These I'm putting here down, they are meaning the masses. These are the masses of the hydrogens which we are talking about. Now you find that whenever you get a sample of hydrogen, always every time you get a sample of hydrogen, you are going to find maybe 12%, let me say 10% is hydrogen 1, and then obviously this one should be bigger. So maybe you're going to find that 70% of the hydrogen you've gotten is hydrogen 1, and then you are going to find that 20% is hydrogen 2, and then 10% is hydrogen 3. So to find the relative atomic mass of hydrogen now, relative atomic mass is going to be given by the mass of the first atom multiplied by the percentage abundance plus the mass of the next atom multiplied by the percentage abundance plus the mass of the next one multiplied by the percentage abundance. We are saying percentage abundance. How much are you going to find that element when you get a sample? So for the first one, the mass of the first one is 1. The percentage abundance is 70%. So we use that as a fraction. So we're going to say 70 over 100. And then you are going to go to the next one. The mass of the second isotope is 2. The abundance is 20. So we're going to say 20 out of 100. And then you go to the next one. The mass is what? The mass is 3. The abundance is what? The abundance is 10%. 10% is 10 out of 100. So this will cancel with this. This 0 also cancels with that. 0 also cancels with that. So 10 into 7, that is 0 0.7. 0 0.7 times 1, it will still be 0 0.7. And then plus 10 into 2. Of course, I can simply say 2 times 2, that is going to be 4. And then 4 over 10, that is going to be 0 0.4. And then we can say 3 multiplied by 1, that is going to be 3. And then 3 over the 10, which is here, that is going to be 0 0.3. And then we are going to add this 0 0.7, 0 0.4, 0 0.3. 7 plus 4 plus 3, that is going to be 14. So we are right 4, remainder 1. And then 0 plus 0 plus 0 is 0 plus 1, 1. So we can see that each of these have got 1 decimal place. So we're going to have 1 decimal place there. So this is going to give us 1.4. This means that this is going to be the relative atomic mass. So if you check on the periodic table like this, you have got A, you have got Z. Remember we said A is what? The proton number. I mean, Z is the proton number, and then A is the mass number. So actually on the periodic table, what we are given is not a mass number, but the relative atomic mass. Because if we say mass number just means the number of neutrons plus the number of what? Protons. Number of neutrons plus the number of protons. For example, if you talk of this hydrogen, the number of neutrons and the number of protons, this is going to give you 1. If you talk of this one, it's going to give you 2. If you take of this one, it's going to give you 3. Now, which one are you going to get and put on the periodic table? Are you going to get a 1 or a 2 or a 3? So, if you check some periodic table, they've got also some decimals. For example, the mass number you are going to find for hydrogen, the mass number is 1.008. Now, when you're talking about the mass number is simply the number of protons plus neutrons. When you add the things, you shall never get a decimal. For example, 2 people plus 5 people, you can't get 7.5 people. No, it's not possible getting a fraction when you are adding things which you are able to count. So when you're talking about mass number, it's simply the things that you are able to count. Relative atomic mass is the average mass of an atom compared to 1 over 12. So the number you see on the periodic table, that is the relative atomic mass. So this is how we get to calculate relative atomic mass. So depending on how much they can give us different isotopes, you are able to calculate. Let's look at another example. We see how we are able to calculate. Okay, so chlorine, we've been told chlorine contains 75% isotope with a mass of 35. This one is 75% with a mass of 35. And then you have got another one which is 25% with a mass of 37. And then the question is, what is the relative atomic mass? So relative atomic mass is given by mass 1 multiplied by the percentage abundance plus mass 2 multiplied by the percentage abundance. Since here we only have two isotopes, so we are just going to end here. If we had others, we would have added mass 3 plus times percentage abundance 3. So the first mass is 35, the abundance is 75, so we're going to say 75 over 100. And then the next mass is what? 37 multiplied by the abundance, which is what? 25 over 100. So this, if we calculate, is going to give us about 35.5, and this is the number that we are going to find on the periodic table for chlorine. So we're going to say chlorine we've written as Cl with a 35.5. It can either be on top or down depending, and then you have got a proton number down here. So I'll repeat, there's a difference between relative atomic mass and mass number. Relative atomic mass, you've seen how we are calculating it, but mass number is simply adding protons and neutrons. So for mass number, you can't have a decimal. The number that is given on the periodic table for each element is necessarily not a mass number, but relative atomic mass. Okay. For example, oxygen, you are going to find oxygen like this, or you are going to have 8 and a 16. This 16 is not a mass number. It's not a number of atoms, I mean number of neutrons plus protons. It is a relative atomic mass. It was found by using this formula. Unless if they've just given you an element like that, they say it has got 8 electrons, maybe 9 protons, determine the number of neutrons like that. So this is what we also need to know. It's very important.